Thank you. All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so it's good to be in this room. I just finished teaching in a class. I don't think the air conditioning was working, so I was dying in there. So I'm glad the air conditioning is working here. Okay, so obvious thing today is that I did finish grading your guys' midterm exams. It took me a little bit longer than I thought. I finished by this afternoon. Average on the exam was just about 40 out of 50. Right, so you guys did well overall, right? So it was a very long exam, and so I wasn't too picky about the specifics of the calculations. I was more looking at how you guys set up the problems and how you formulated everything, whether you assembled in the right places. That's kind of what I looked at a lot. So I think overall you guys understood that pretty well. So again, remember, this is only midterm one of two, and so if you didn't get a score you're happy with this midterm exam, just know that we have the second midterm. Second midterm is going to take place after spring break, obviously. And if you do better on the second midterm, it will count for a higher percentage of your grade. Okay. So even though this is a big part of your grade, not discounting that, but there's still ways to make it up for the next exam and obviously with the final project as well. Okay. Okay, and so plan for today is we're going to finish up the example that we started on Tuesday on finding approximate solutions to weak form boundary problems. So we kind of stopped halfway, so I do want to finish that. And that's actually kind of a good segue into our next topic, which is finite element forms, right? So, kind of like what I've mentioned before, is that, second half of this class, we're going to be covering more traditional finite elements. And so this is kind of how finite elements is actually formulated inside commercial software like ANSYS, right? Direct stiffness method has its place as kind of like just like an educational tool, but no one really uses direct stiffness for practical problems. So, from here on out for the rest of the class, this is kind of more traditional FEA that you would kind of learn in a typical course. Okay. All right. Any questions I can answer before we get started? I just remembered just now that I am going to post the solutions for this midterm, but I have not done that yet. So I will probably do that probably sometime tomorrow. Okay. Okay. All right. So let's go ahead and get started. Okay. So to get started today, I'm just going to kind of scroll up here a little bit just because we did start an example, right? So you don't have to write this down again just because it should already be in your notes. Okay. But we were looking at this particular problem right here, and we wanted to find its solution. We wanted to find the solution to the strong form and a solution to the weak form of this problem, particularly an approximate solution to the weak form, right? So we have a one-dimensional heat flow inside a rod here, right? So this rod is about 5 meters long. It's subjected to a fixed temperature on the left-hand side. It's subjected to an adiabatic condition on the right-hand side. So that means that there is no heat flux. So the derivative of the temperature is going to be 0 and is subjected to a uniform heating, or not uniform, a uniform heating function S of x that's going to be distributed all throughout and has a value of x squared divided by 5. Okay. It has a thermal conductivity of 2, a cross-sectional area of 0.5. And so, taking those into account, we solve for the strong form solution. So for that, we just took our differential equation, we just integrated it twice. We got our solution here. Okay. We plugged in the boundary conditions and we got this solution here. Okay. And then we wanted to solve the same problem, but from the weak form. Okay. And so what we said is that, to solve for a weak form solution, we are going to first assume a form for the solution. And so for this particular problem, we're assuming a quadratic form. So we're going to assume that our temperature and our weighting function take a generic quadratic function form. So that's a0 plus a1x plus a2x squared. And for our weighting function w of x, this is b0 plus b1x plus b2 squared. Okay. Now, the first thing that we conceded, first thing that we kind of notice is that, by making this assumption that our solution is going to be quadratic, we're kind of conceding the fact that, our quadratic function is never going to quite be equal to the exact solution. Because the exact solution has a term that is x to the fourth, right? So you have minus x to the fourth divided by 60. So it's impossible, with our given form to reach that form there, right? So we can only go up to x squared. And so no matter what we get from this solution here, it's never going to be exact, but we can see how close that we're going to get. Okay. And so before we actually plug into the weak form of the solution, we do have to apply our Dirichlet boundary condition. And so for this particular problem, we have one Dirichlet boundary condition that's applied on the left-hand side. And so we're going to apply the fact that our temperature at x is equal to 0 is equal to 25 degrees Celsius, right? So the way we did that was we took our assumed form, we plugged in x is equal to 0, and we set it equal to 25. And that allowed us to solve for the values of one of the coefficients, okay? And so we found that A0 is equal to 25. And then applying the same boundary condition to the weighting function, we can of course, solve for a solution to one of the coefficients there as well. But remember, the difference is that for the weighting function, we require that our weighting function disappears at the location of the Dirichlet boundary condition. So we set W of x is equal to 0 is equal to 0. And that gives us B0 is equal to 0. Okay, and so that's where we stopped, right? And so if we kind of pick up where we left off there, right, we can see that. So right now, our guess for T of x and W of x are, okay, so T of x is equal to 25 plus a1 times x plus a2x squared, and W of x, right, B0 is equal to 0, and so this is B1x plus B2x squared, okay? Okay, so we've solved for one of the coefficients, and so we solved for A0, but in order to complete this problem, we also need a solution for A1, and we need a solution for A2 as well. And so the way that we're going to solve for these is that we're going to plug these expressions into our weak form of our boundary value problem, and then kind of work through the algebra, work through the calculus, and eventually we're going to get expressions that we can use to solve for A1, A2. Okay. All right, so that's the game plan, right? So let's write out our weak form one more time. So this is the weak form of 1D heat conduction. All right, so for this we have integral of from 0 to L, right? So when we're integrating across the entire domain, so we're integrating from x is equal to 0 to x is equal to L of dw dx times k times a dt dx dx, okay, is equal to integral from 0 to L of w of x, bless you, s of x dx plus our Neumann boundary condition terms. So you have w times k times a dt dx. Okay. And we're going to evaluate this at the location of our Neumann boundary condition. For this symbol right here, this gamma n, this is the location of a Neumann boundary condition. Which in our case, we do have a Neumann boundary condition. Our Neumann boundary condition is that x is equal to L. So we're going to evaluate that term in the square brackets at x is equal to L. Okay. Okay. So by plugging everything in here and kind of working through all of the simplification and the integrals, eventually we're going to get expressions that we can solve for A0 and A1 and A2. Okay. Now, B1 and B2 are obviously going to be part of our solution here, right? Because we're plugging it for W, but we don't really care too much what W of x is. W of x here is mostly just a tool that we're going to use to solve T of x. Okay. So W of x will be there. And in fact, it will be part of the solution, but the actual values of B1, B2 are not really that important to us. Okay. Okay. All right. Any questions on this, on just the setup before we kind of start diving into the algebra here? Okay. All right. So let's go ahead and plug in. Okay. All right. So the first thing that we have here is we have dw dx. Right. So let's evaluate this term first. So we have integral from 0 to L. So dw dx, we're going to take our current guess for w of x, which is b1x plus b2x squared. We're going to take its derivative. Okay. And so that's going to be b1 plus 2b2x. Okay. We have k times a, but for this particular problem, k is equal to 2 and a is equal to 0.5. So those two quantities are just going to cancel out. Or they don't cancel out, they equal 1, which essentially cancels out. Okay. Next, we have the derivative of t. So we have dt dx. And so we take the derivative of our current guess for t, and that is 25 plus a1x plus a2x squared. So we take its derivative, we get a1 plus 2a2x dx. Okay. Okay. Good. This is equal to, now we have the integral of w of x times s of x from 0 to L. So let's take the integral from 0 to L. W of x, we're just going to write in the expression of w here, so there's no derivative. And so that's going to be b1 times x plus b2x squared. Okay. So that right there is w of x. We're then going to multiply that by s of x. So s of x is x squared divided by 5. Okay. Dx. All right, and then finally, we have the Neumann boundary condition term. So we're going to evaluate everything in that expression at x is equal to L. So plus w at x is equal to L multiplied by k times a, right? So in this particular problem, k and a are constants, right? So they don't vary. But in other problems you'll see on your homework eventually, your k and a could vary with x, and so make sure that you plug in the correct value for x for these expressions. Okay? So if these change with x, make sure you plug in the appropriate value for x when you're evaluating this boundary term. Okay. All right, but here they don't vary with x, so we're just going to plug in their constant values, and this is multiplied by dt dx at x is equal to L. All right, so let's go ahead and simplify this. And so actually, I'm going to start from let's start from the right and work our way left. Okay. So first thing we have here is our Neumann boundary condition term, right? In particular, we have dt dx at x is equal to L. Okay. So let's go back to our problem and let's see what this value is based on our boundary conditions. Okay. Okay, so we come back up here, right? we know that on the left-hand side of the domain, or the right-hand side, excuse me, the right-hand side of the domain, we have derivative of t is equal to 0, okay? And so that's convenient. So if it's equal to 0, that means that last term there is just going to cancel out, okay? All right, and so since dt dx at x equal to L is equal to 0. Okay, so that's nice. So that's one less term for us to kind of worry about. Okay. Okay, so now let's work on the two integration terms there. So let's work on the first one first. Okay. So I'm just going to work on this one, but we're not going to forget the other one as well. Okay. Okay, so for this one here, let's go ahead and FOIL that out. And so we have integral from 0 to L of b1 times a1 plus 2b2 a1x plus sorry, I got confused. Plus 2a2 b1x plus 4 a2 b2 x squared dx. Kind of did that FOIL in kind of a weird kind of a weird way, but that should be correct there. Yep. Okay. All right, so let's go ahead and perform these integrals. So, there's a lot of terms here, but most of them are constants, right? And so we perform these integrals, we get b1 a1 times x plus b2 a1 x squared plus a2 b1 x squared plus 4 over 3 a2 b2 x cubed. Okay. And we're evaluating every term here from x equal to 0 to x is equal to L. Okay. And in fact, since we're at this point here, we're going to plug in numbers anyway. Let's go ahead and plug in for x equal to L, right? So we know for this particular problem, the length of our rod is 5 meters. Okay, so let's just go ahead and plug in x is equal to, or L is equal to 5. Okay. All right, so second part of the lower bound here is 0, and so that's just going to cancel out, right? And so what we get is b1 a1 times 5 plus 25 b2 a1 plus 25 a2 b1 plus x cubed, so 5 cubed is 125. 4 times 125 is 500. So that's 500 over 3 a2 b2. Okay, so that's our first integral there. So we're just going to leave this alone for now. We are going to come back to it, but let's kind of leave it at this point for you. Okay, so there's nothing more that we can continue on here.
For this first term, when did we drop off the Ka term?
So Ka in this case was their product was just 1. So K is 2 and A is 0.5. Okay. So I think just from this part right here, we say that their product here is 1. Okay. Mm-hmm. Yeah, good question though. But okay, yeah, normally you'd keep it, but for this particular case, the equal 1. All right. Any other questions on how we got to this point here? Okay. All right. So let's go ahead and let's do the other integral now. Okay. So the other integral in our expression was this guy right here. Okay. So let's do integral from 0 to 5 of b1x plus b2x squared multiplied by x squared divided by 5 dx. Okay. Okay, so let's go ahead and distribute the x squared over 5. And so we get integral from 0 to 5 of b1 x cubed over 5 plus b2 x to the fourth over 5 dx. Okay, so let's go ahead and perform this integral. This one's a little bit less cumbersome just because we have less terms here. But we have b1 x to the fourth over 20 plus b2 x to the fifth divided by 25. Evaluated from 0 to 5. Okay. All right, so let's just go ahead and plug in for this, right? And so for this, we get b1 x to the fourth power there is 25 times 25. So we have a 5 that's actually going to come in from the denominator. That's going to cancel that out. And so that's going to be 125, which is 5 cubed all over 4. Okay. Plus b2 times x to the fifth power divided by 25. Let's make note that 25 is 5 squared. So we have 5 to the fifth power divided by 5 squared. That's just going to be 5 cubed. And so this is going to be 125 times b2. Okay. So now that we've evaluated our two integrals, right? If we go back to our original equation, we know that these two integrals are going to be equal to each other. So let's go ahead and set these two expressions that I've underlined, right? So the top underlying expression, that was from our left-hand side integral with the derivatives of our solution function and our weighting function. And the bottom here, that's our right-hand side that's our right-hand side term that's coming from our source. Okay. Okay. So we set them equal to each other. We get 5b1a1 plus 25 b2a2 plus 25 a2b1 plus 500 over 3 a2b2. Okay. I'm sorry. This first 25 here is b2a1. I apologize. So make sure that's b2. We should have just one combination of every term there. Okay. And then on the right-hand side, we have 125 over 4 times b1 plus 125 b2. All right. So it looks like alphabet soup there. So it looks like we have a lot of A's and B's kind of going around. But we have actually everything we need to solve for our solution, right? Because remember, for these problems, we don't care all too much what the result of our weighting function is. But you can see here that it is going to be a tool that we can use to solve for A1 and A2. Okay, so that's really what's important. Okay, so to solve this, what I'm going to do is that on the left-hand side, I'm going to group like terms, but I'm going to group like terms according to the B coefficients. Okay, so first we have the B1 terms. The B1 terms are 5A1 plus 25A2, okay, times B1 plus Then we have the B2 term, so that's 25A1 plus 500 over 3A2 times B2, okay? And then on the right-hand side, we still have our 125 over 4B1 and our 125 B2. Bless you. All right, so by doing so, maybe you can kind of see what we're going to do next, right? And so, we have two unknowns, right? So we have an unknown A1 and an unknown A2, right? So that tells us that we need two equations to solve for the values of A1, A2, right? And if you look at the structure of the equation so far, right, we kind of have that, right? And so if we look at this, right, this is everything that's multiplied by B1 on the left-hand side. And on the right-hand side, we have something multiplied by B1, okay? And then also, we have this equation that's multiplied by B2, and we have a B2 term on the right-hand side as well, okay? So if we set that our two expressions on either side, according to their B coefficient, equals to each other, that's going to give us two equations to solve for our two unknowns, A1 and A2. All right, and so our first equation is 5A1 plus 25A2 is equal to 125 over 4. And then our second equation is 25A1 plus 500 over 3A2 is equal to 125. Okay. All right, so two linear systems for two unknowns, right? So for a relatively simple system like this, you can just solve it by substitution. And so, you can solve for one of the variables and just plug into the other expression, right? So maybe one thing I would do is I would solve the first expression. So I would say the first expression is 5A1 is equal to 125 over 4 minus 25A2, okay? I would then take this expression and plug it in here, okay? So that will eliminate A1 from the second expression and then allow us to solve for A2, right? And then once we have an answer for A2, then we plug it back in and solve for A1, right? So for a 2x2 system like this, you don't really have to do anything special. But if you're lazy like me, you can also just punch this into MATLAB, right? Right, so if we solve this via MATLAB, we get our two answers. We get A1 is equal to 10 and A2 is equal to minus 0.75. All right, and so now that we have A1, A2, we are now done, right? So let's go ahead and plug these back in to T of X. Okay, and so we get T of X is equal to, we have A0, so remember A0 was 25, that's what we found from our Dirichlet boundary condition, so let's not forget that, okay? 25 plus 10 times X, so that's A1 times X, minus 0.75, which is A2, X squared. So this right here represents the best possible quadratic function that solves our original boundary value problem. Okay. Now remember, it's not the exact solution. So the exact solution in this case does have x to the fourth, but this does come as close as we can with the quadratic function. Okay. All right, any questions on how we got this result here? Good. Okay, so let's compare this. Okay. Right, so if we do a versus with the exact solution, right, so our exact solution, remember, for our strong form was T of x is equal to x to the minus x to the fourth divided by 60 plus 25 over 3 times x plus 25. Okay, so this right here, this was our exact solution to our strong form. Okay, so you can see the functions do actually look quite different. And so our strong form solution does not even have any quadratic terms. And so, our quadratic term is kind of doing its best to emulate that x to the fourth power, at least within our domain. Okay, and so if you plot them, then that's kind of where it kind of looks most interesting. Okay. All right, and so if you plot your approximate solution, you're going to see it might look something like this. Okay. Whereas the exact solution, maybe looks something like this. Okay. So there are differences, right? So there's no way that an x squared term is ever going to equal x to the fourth, right? But it does capture the same kind of trends. Okay. Okay, so I think this was a good example to kind of show this kind of whole process of finding approximate solutions. And it kind of illustrates that, an approximate solution is always going to be approximate, right? There are situations where your approximate solution can match your exact solution, but usually those are rare. Okay. So if our approximate solution is never going to be exact, right, then why would we even bother solving for an approximate solution, right? So remember, for this particular case, in our 1D case, we were in a situation where we could solve for the exact solution because we have a simple one-dimensional problem with simple boundary conditions and simple body force, right? But we're not always going to be in that position. So we cannot always solve for the exact solution, okay? And so that's especially true when we move on to multi-dimensional finite elements, so 2D or 3D. Okay? Right? Because you're talking 2D problems, you're talking 3D problems, those are partial differential equations that you're looking at. So, exact solutions for those problems are very rare and often, way more trouble than it's worth to actually solve for the solutions. Okay. So even though our approximate solution, in one dimension does not seem that useful, this methodology or this technique of, first assuming a solution value and then plugging it in and then solving for the best form is actually going to form the basis of how we solve for our finite element solutions, which is what we're going to do in, right after this. Okay. Okay. Any final questions on weak form solutions to boundary drive problems? Okay. All right. So let's go ahead and move on to the next set of lecture notes, which is on finite element formulations. Okay. Okay. All right, so that was kind of a nice break from finite elements, right? So we've kind of spent the last 2 lectures or so, 2.5 lectures, talking about just math essentially, right? But this is a finite element course. We got to bring it back to FEA at some point, right? And so finite elements, right, in its kind of purest form, right? ultimately, finite elements gives us a way to solve differential equations numerically. Okay? So at its core, okay. So I think, nowadays when you mention FEA, you mention finite elements, I think people associate it with the commercial softwares. So they think of things like ANSYS, they think of Abacus, they think of SolidWorks simulation, things like that, right? But at its core, the whole reason FEA was developed was a way to solve these differential equations, okay? It just so happens that, a lot of physical phenomena that we're looking at in an engineering application in an applied science perspective, their behavior is governed by these differential equations, okay? And so that's kind of how FEA kind of evolved, where, FEA developed as just a way to solve differential equations. A lot of physical systems just obey differential equations. That's how they're designed. That's how their physics work. And so FEA is now used to solve or analyze those physical systems, okay? Okay, so what's the idea? So how are we going to do this, and how does that connect to everything that we talked about so far? Okay, so FEA, the way that it solves for the solution is basically the same way that we just did in our previous example, right? So FEA seeks an approximate solution, right? An approximate solution based on an assumed functional form. So just like we did in the previous problem, when we solve for finite element solutions, we are going to assume a functional form. Usually it's going to be a polynomial. That's kind of what works out the best. And then we're going to work it through our weak form and then solve for its solution. Okay. The biggest difference is that instead of solving for a weak form solution that's valid across the entire domain, we are instead going to break up our solution on different elements. So do this for each element. Okay. Okay. And so, for a typical 1D domain, and we're going to start in one dimension, okay? Eventually, after spring break, we are going to work ourselves up to 2D and discuss the theory of 2D finite elements, okay? So let's say that we have a domain that's given by a one-dimensional line like this, right? So this would be like x is equal to 0, x is equal to L, right? Right. So we just saw in the previous example, right, that we can solve for an approximate solution on a domain like this, right? Right. And so if we were to take this entire domain as its own one domain, right, we can solve for an approximate solution. Right. But because we're approximating over such a large domain, right, we're kind of subjected to a lot of errors at the same time too, right? And we just saw that. And so, if you compare that to, a corresponding exact solution, right, there may be some quite a bit differences because we're approximating over such a large domain. don't know how it's making that sound. I don't have Discord on this computer. Okay. All right, so the idea with finite elements is that we like the idea, we like the concept of an approximate solution, because as our differential equations get more complicated, right, we're going to need to get an approximate solution because we can't find exact ones. But we want to mitigate this issue. We want to mitigate this issue of the more we approximate, the larger the errors are. Okay, so the solution to this was to say, instead of finding one approximate solution that spans your entire domain, let's find several approximate solutions on different subsections of a domain, okay? So you're going to take your domain, right? So we have our same line here. And instead of solving it for one kind of big, long domain, we're instead going to break it up into elements. Okay. So on this side here, we've broken up our domain into different elements. And then on each of the elements, we're going to solve for a separate approximate solution with slightly different conditions. Okay. Right. And so on each of these, we're going to solve for an approximate solution. So it may look something like this, right? Right. So now our approximate solution is kind of piecewise across each of the elements. And the idea is that by doing so, and then, by hopefully discretizing enough, by making our mesh fine enough, we approach the exact solution much more closely. So, you may get a situation that looks like this. Okay. Okay. All right, so there's less approximation that we have to do because we're solving multiple solutions at once. But the downside is that we do have to solve for multiple solutions at once, which is also kind of cumbersome. Okay, but the nice thing about this approach, and which is going to be the subject for the final project, is that this approach of kind of solving pretty much the exact same equation on several elements, just with slight differences on each element, it really lends itself really well to a computer algorithm. Okay, so just like you guys just did. On the ANSYS activity, the second part where you wrote your trust code, right? A lot of finite element algorithms and a lot of finite element methodology, it's honestly a lot of repetitive computations, which is what computers are really, really good at. Okay. So that's eventually where we're going to go, but there's a lot for us to kind of build up along the way. Okay, but that's essentially kind of the idea that we want to do. Okay. All right. Any questions on this so far? Okay, all right. So let's go ahead and start building up this this idea, right? Okay. So first thing we're going to discuss is the requirements of our finite element solution. Okay, so because our finite element solution is going to be a piecewise function, right? There are certain requirements that we have to fulfill in order to make sure our solution is valid. Okay, all right. So let's talk about those requirements. Okay. Okay, so first requirement that we are going to state is the requirement of continuity. All right. So remember, the way that we're defining our FEA solutions is that, we're defining essentially solving for a separate solution on each individual element, okay? But when you go from one element to the next, right, you should not have any discontinuities in your solution, right? So going from one element to the next, your solution value should be continuous. Okay? So there should not be any sharp discontinuities in your solution, okay? Right? But continuity actually goes a step further. So, on the basic level, your solution itself should be continuous. So there shouldn't be any kind of, kind of sharp changes in your solution going from one element to the next, right? But also, for certain formulations and certain approximations, we may also require the derivative of the solution to be continuous across the element boundaries. Okay? All right, and so in fact, there's a rule for this, right? And so there's a way that you can kind of determine what the continuity requirements are, and it's going to be based on the weak form of your solution. Okay. So if let's define some integer k. So let's say if k is the highest order derivative of the weak form, okay. All right, so k is, so let's say that the highest order derivative of your weak term, if your weak form is 2, then k is 2, okay? Then we require the first k minus 1 derivatives to be continuous across element boundaries. Okay. So if you think back to our typical weak forms, so the weak forms that we discussed, in the previous class, right? The highest order derivative that we had in those weak forms for elasticity and for heat transfer was 1, right? And so that was kind of a big point of doing our weak forms, so that we went from a second order differential equation to not a first order differential equation, but a weak form that only had first order derivatives. So we had a first order derivative of the weighting function multiplied by a first order derivative of the solution, okay? So since k for our case is 1, that means we're actually in a situation where we don't require any of our derivatives to be continuous, okay? Oops. So for heat transfer, or say for elasticity and heat transfer, okay, k is equal to 1, right? That's kind of what we showed, in the last class, right? So if k is equal to 1, that means none of the derivatives have to be continuous. okay, which is pretty huge actually. So that's a very, very nice feature of our solution that we have, that we can actually have discontinuous derivatives, okay? It does look a little bit weird, right? So if you did compute the derivative of your solution, you may get kind of sharp changes or sharp kind of sharp drop-offs of the derivative, but it doesn't mean that our solution is going to be invalid. Okay, so the only thing we require is that our solutions be the same, right? Or the solutions are continuous. So there's no sharp changes in the solution as we go from element to element for our finite element solution. Okay. Okay. All right. Any questions about continuity? All right. So actually, one last note. So the way that we're going to enforce this is that we're going to enforce this by the fact that for any element that shares a particular node, right? So for any given finite element mesh, a node is always going to border at least two elements here, right? So this node here that I've kind of highlighted, right, is shared between this element and this element, right? It's the node that's kind of in between, okay? So the way that we kind of enforce continuity is by just enforcing the uniformity of the nodal solutions. Okay. So for every element that shares a particular node, right? In 1D, it's only going to be two elements because you can only make so many element shapes in 1D, right? So for both of the elements that share a particular node in 1D, they have to have the same nodal solutions at those nodes. Okay. In 2D and 3D, it does get a bit more complicated. You do get situations where you can have, 3, 4, 5, 6 elements that share a particular node, right? And so that does get more complicated there. We'll kind of cross that bridge when we get there. So, but for now, you can think for every node that's not on the boundary, right? So every node that's not on the boundary is going to have at least two elements, or going to have exactly two elements that have to share that nodal solution. Okay. Okay. All right. So that's the continuity requirement. That's probably the most important one for what we're going to discuss. Okay. The next requirement that we have is called completeness. Okay, so the completeness requirement actually has to do with our assumed functional form. Okay? And so the completeness requirement says that the assumed functional form should be a complete function, which sounds like a very cyclical kind of argument, but I'll kind of define complete function in a second. Okay. Right, so a complete function is essentially a function that models all of the behavior, lower order and higher order, for a given particular order. Okay. So, a lot of times we do this implicitly, especially if you're doing polynomials. Getting a complete polynomial is very straightforward, right? So for example, right? For a second degree polynomial, right, better known as a quadratic function, a complete quadratic function would not only include the x squared term, but also include the constant term and the linear term as well. Okay. So t of x is equal to a0 constant term plus a1x linear term plus a2x squared. Okay. So not only do we have the x squared term, but we also include all the lower order expressions as well. Okay. Okay. Right, so that's kind of part one of the completeness requirement, is that whatever we choose for our approximation, it has to be a complete function. Okay. Now the next question is, how high of a degree do we need for a particular assumption? Okay. So the required degree of the polynomial So our polynomial, our approximation has to be at least matching an order of the highest derivative in our weak form. Okay. So you can see this is another place where our weak form kind of comes into play, right? So for our weak form that we're considering, the highest order derivative is just one. And so that means we only need a first degree polynomial to get a complete solution. Okay. So for derivative order of one, which is what we have, okay. Now, of course, you can go higher than this, and so this only sets the minimum required degree. But if you wanted to go higher, like I said, you want a quadratic function or a cubic function, you can definitely do so. But the minimum that you need is just a linear function. Okay? So linear function is just t of x is equal to a0 plus a1 times x. Okay, which you can see is a huge simplification from the quadratic. And so that's one less term to worry about. It's going to make our integrals very simple because we're just integrating linear terms here, right? So this is actually a pretty huge kind of requirement that we have. So we don't have to go higher than linear, which is very, very nice. Okay. Okay. So essentially, there's kind of two upshots from this from these requirements here. On the one hand, we have to make sure that we match nodal solutions, right? And so that kind of gives us a sense that these nodal solutions are going to be important when we derive our finite element forms, right? And the other important consideration here is that we only need a linear function. And so when we're making our approximate solutions, or we're assuming a functional form, we only have to go up to linear, which is very, very nice. Okay. All right. Any questions on this? Okay. All right. So the last topic that we'll go over today is the concept of a shape function, which is a concept that we'll return to over and over and over again as we discuss finite element forms. Okay. All All right, so now that we know the requirements for our solution, let's actually kind of put this in practice, okay? So let's consider a very simple one-dimensional element that has two nodes. Okay, so you just have a very simple line here, okay? We know the x coordinates, or we know the locations of each of the nodes. And so on the left-hand side, we have x1. Right-hand side, we have x2. Okay. Right. The other thing that we know, or the other thing that we're going to assume that we know, and we're going to need to enforce continuity, is let's assume that we also know the nodal solutions. Okay. So left-hand side, we're going to have, I'm going to switch notations a little bit. We're going to have U1 and U2. Okay. Where these are the nodal solutions. Okay. Okay. So remember, the nodal solutions are the solutions to our boundary value problem defined at the nodes. Okay. So you can think of the nodal solutions as kind of like our solution. We just sample at those particular locations. Okay. Okay. Next thing that we're going to do is we're going to assume a linear approximation. And so our linear solution we'll say is UE, right? So I'm going to use a superscript E here to denote that this is the solution that's going to be assumed on this particular element. Okay, so E for element of X is equal to A0E plus A1E times X. We have our very simple linear function with only two unknown coefficients, A1, A0 and A1. Okay, so we have a very simple case here. Okay? And so just like we did in the first example today, we want to solve for the coefficients A0 and A1, okay? Right? Because if we can get expressions for A0 and A1, that'll give us our solution for this entire element here, okay? Okay. All right, so to solve for the solutions for A0 and A1, we're going to invoke our continuity requirements. Okay? So because of continuity, right? So because of continuity, our assumed solution has to match the nodal solutions at x1 and x2. Okay. All right, and so those essentially will become our Dirichlet boundary conditions, right? Because we're assuming, or what we're going to enforce is that UE at x1 has to equal U1, and then UE at x2 has to equal to U2. Okay, okay, so we have UE of x1. So we're just going to plug in x1 in for x for our assumed solution here. So it's going to be A0E plus A1E times x1. Okay. So by our continuity requirements, this has to equal to U1. Okay. And then UE at x2 is equal to A0E plus A1E times x2 is equal to U2. All right, so once again, we're in a situation where we have two equations, right? So we have equation one, equation two, the U1, U2 equations, and we have two unknowns, which is A0 and A1, okay? This one's a little bit more annoying to compute, just because it's all in symbols, right? But thankfully, our two equations here are quite similar to each other, okay? So to solve for the solution, one way that you can do this very simply is we can take our first equation and just subtract it from the other equation, okay? So if you've never seen this before, we're basically just taking all the terms on the left-hand side, subtract all the terms from the first equation, minus the terms from the second equation, and then same thing on the right-hand side, okay? So what that's going to give us is A0 times E plus A1E times X1 minus A0E plus A1E times X2 is equal to U1 minus U2. Okay, so I'm literally just taking the entire second equation and subtracting it from the first equation. Okay. All right, and so by doing this, we can see, and the reason we did this is I noticed that there's A0 in both equations, right? And there's no coefficients. And so by subtracting these two equations, the A0s are just going to simply cancel out, okay? And then what we get is A1E multiplied by X1 minus X2 is equal to U1 minus U2, okay? And so this is a very simple expression, and we can get A1E is equal to U1 minus U2, all divided by X1 minus X2. Okay. All right, so now that we have A1, we can plug this back into either equation and solve for A0, okay? And so, I'll kind of let you guys fill in the details. It's just kind of busy work from there, right? The interesting thing here is that, you can get two different expressions for A0. If you plug into the second equation, you're going to get an expression for A0 that involves U2 and X2. Or if you plug into the first equation, you get an expression for A0 that involves U1 and X1, okay? Now it all kind of balances out in the end because A1 here also depends on U1, U2. But I did want to kind of make that point just because it seems paradoxical at first that you can kind of plug in to either equation and get the same result. But it's because we have U1 and U2s and the A1s, and then it all works out, right? So either one you plug in, it works out. Okay? And so what you get from that is A0 is equal to X1 U2 minus X2 U1 divided by X1 minus X2. Okay. Okay, so I am skipping ahead a little bit just because I do want to get to the conclusion of this before we end for the week. Okay, so let's go ahead and plug both of these back into our assumed solution here. Okay. Okay. And so we plug back in, we get UE of X is equal to X1 U2 minus X2 U1 divided by X1 minus X2 plus U1 minus U2 divided by X1 minus X2, okay, multiplied by X. All right, and so that is our very first kind of finite element solution for a given element here. Okay. All right, so let's rearrange this a little bit. So let's rearrange this just to make things a bit more clear for us. Okay. Right, and the way that we're going to rearrange is that we're going to group like terms according to the U terms. Okay. All right, so we group those like terms, we get UE of x is equal to, so let's do the U1 terms first. So U1, we have x minus x2 divided by x1 minus x2 multiplied by U1 plus, let's see, we have x1 minus x divided by x1 minus x2 times U2. Okay. Right. So all I did was I just rearranged the terms. So I just kind of swap some terms around so that we have one entire expression multiplied by U1 plus another entire expression multiplied by U2. Okay. So the reason I did this is that these quantities in the parentheses, right? These are what we call the shape functions. And we name these shape functions according to the nodes where the shape function is equal to 1. So this first one here, we call this one n1 of x. Okay. The second shape function, this second expression here, we'll call n2 of x. Okay. And so what you get, right, based on those approximations is that UE of x is equal to n1 of x multiplied by U1 plus n2 of x multiplied by U2. Okay. Right. Where we've essentially taken our approximation or approximate function for this element and put it in terms of these shape functions. Okay. Now we'll go over the properties of the shape functions much more next time, but I do want to make kind of one very quick observation. Okay. So n1, right? When you evaluate a shape function at the node where it's specified, you should get 1, right? So if you evaluate n1 at x1, okay, you get x1 minus x2 divided by x1 minus x2 is equal to 1. Okay. But if you evaluate a shape function at a different node, so a node that is not corresponding to its number, you should get 0. Okay. So n1 at x2, right? We plug in x2 in for n1, we get x2 minus x2 divided by x1 minus x2 is equal to 0. Okay. And you can do the same exercise for n2. So n2 you evaluate it at x1, you should get 0, but n2 evaluated at x2 is equal to 1. Okay. So this property of shape function is actually going to be retained once we even go to the higher dimensions. So once we go to 2 dimensions and 3 dimensions, these shape functions will have these same properties. The only thing that's going to be different is that our shape function is going to have a different form. Okay. But what you're going to see next week when we come back is that, there's a very good reason I'm formulating these expressions in terms of the shape functions, because our shape functions are going to form the basis of our element stiffness matrices that we're going to compute for these elements here, right? So even though we're away from the direct stiffness method, you're not going to escape element stiffness matrices. They're still going to be there. It's just that the way we compute the element stiffness matrices is going to be different because they're going to involve these shape functions. Okay. All right. Any final questions before we wrap it up for the week?
You scroll just a little bit.
Sure. Thank you. Mm-hmm. Okay. And so if there's no more questions, I do have your exams, and so you guys can come up and pick it up. Right. Please look at the exams. Please look at my comments. And so I think most of the comments I made were on the conceptual questions. And make sure I added up the points and everything correctly too. Okay. So thank you guys for coming this week. I hope you guys have a good weekend, and I will see you all next week. For Anselm, we also. Yes, yes, please. So if it's not allowing you to submit a MATLAB file, I'll go back and change it right now. But yes, please do submit your M file. Yeah.
Publish it at the end.
If it's just part of the PDF, that's fine. Yeah.
A question about the answers.
Yeah. Okay. I will come then.
Modify this code so that probably drag somebody in.
Yeah.
Do you agree on that?
Yeah.
You already know it.
It does need to, so think about your trust elements, right? So the way you compute the trust elements fit the same. The cross-sectional area divided by the length. And so you need like you need those ones. But the one thing you don't need is
And I knew what it was once it was done.
no, you need that. You're not going to use it.
48.
Yeah, so so once you start to do stuff for code.
I don't know why I thought frames. I'm like,
Yeah, I made a mistake.
Right, so now any reference to where but this is where most of your changes.
She not 438?
yes.
I think I know. I think she's
So different.
Yes.
So place all this code here with
I meant it. Yeah.
So they are gonna be simpler. right?
Well,
So
I
it's
assume-
quite complicated because they're.
I never really saw her.
But for a trust.
I think she was one of those like
science.
What? So,
They don't think.
it's still like a. I'm not too much.
Oh yeah. I'll be honest with you.
I think everybody been at.
If I had that little extra time I worked on. I didn't get money.
Yeah,
Points
so
on
just
it.
remember, so trust is not. That's reflected.
That's all I
I
say.
mean, it is
Trust is about-
same little.
And then that affects.
Yeah, it was.
Well, actually, it's top one. What?
You
mentioned that. Dude, it's.
Will be find the size of those.
Oh.
Yeah, pretty much.
I still don't get
That's
that.
for a frame.
Oh, okay.
For a trust.
Use differently for like those.
Yeah.
I didn't want to be that guy. I'm like,
Or like a collaboration.
we came out. What we talked about, I was like, why you were still there? I was like, oh, shit. Like I thought I was there. And I was like, I'm like, what are you doing? There's people
The
that
way you do is like.
Yeah.
The research that you're doing.
And then save as just
Is
a.
there a hack? Yeah, hack. I know you're right.
I just turned it
Is
off.
there a research paper?
It was locked. I think
See where
it's
one,
one.
see where.
Yeah, 438. You should. Oh, yeah.
It's fine. Yeah. It's just me.